So we are on to the final example. Final example of the real ideal paradigm. This one is involving the two-party board game Battleship. And so let's start, and this time, instead of using cryptographic security, we're using PL security, PL techniques or mechanisms to support or to obtain security. So let's start by reviewing where we got to last time. And so we have an architecture that looks like this. There are two human beings who are connected to clients. The clients are connecting by a TCP connection to a server that within it has two players that are operating on their behalf. The players are talking to a trusted referee, and the referee is holding the two players' boards. So the referee can say to the player one and player two, give me your initial boards in some sequence. It can tell one of them, well, I guess it says here that the first client to connect gets to shoot first. So the referee can say to this player, what's your first shot? It can then update the opponent's board according to that shot, let the player know what the result was, let the opponent know what cell of the board was hit, and then let the second player shoot, and so on. And the game progresses like that. So we had an implementation in concurrent ML of this trusted referee that holds both of the player and updates both of the players' boards, enforcing the rules of the game. But we were also interested in trying to reduce the trusted computing base by splitting the referee into mutually distrustful player interfaces, so like this. And, well, what you want here is that these are using some kind of protocol to communicate with each other. You want that this still works the same from the player's point of view. But we're trying to think, well, suppose one of them deviates from the protocol, does something it shouldn't be doing, tries to learn more from the protocol than it should be able to learn, then how can we define when from the other player interfaces, the honest one, that they're still secure? And that's where we reached into the real ideal paradigm as a way of trying to get a handle on that. So this is the real world, this is the ideal world. Here we have the good player interface and a possibly malicious one. So here we are interacting, we think we're interacting with the client of the good one. This channel here could be also behaving, this could just be another copy of G, and this could be just the normal stuff that's going on, or M could be trying to exfiltrate information about G's board that it's not entitled to know, or it could be being told by the adversary to try to cheat in some way, to maybe conceptually move its ships on its board after it's supposedly committed to a board. So that's what's going on over there. So in other words, this traffic here, it might be just the normal stuff. It could be anything else. It could be whatever the adversary, which is playing the role of the client of the malicious party, whatever it wants to achieve could be going on in that channel. So how do we try to define the ideal world? Well, using the model referee, as we talked about before, is a good first go at this. It's holding the two players' boards, it's enforcing the rules of the game, this honest party communication, what do you want to shoot next? And then communicating the result of the shooting, or saying, well, the opponent did this shooting, and letting the client know that. That's just the normal stuff. But in this position here, the model referee is talking to a player, and the player is actually a simulator. The simulator is sandboxing M within it, putting it in a position where it can't directly talk to the adversary. It can't directly work with the internals of the model referee. It from the model referee's point of view, it's just a player. And so information flows from here to here. So this can be asked, well, where do you want to shoot next? The model referee updates this player's board according to that shooting and lets the simulator player know what happened. And so that's information about the opponent's board that's flowing up like this. At the very beginning, this is going to have to commit to the initial board of the malicious player. And so then that's the one that this player over here can shoot against. And so this is not completely precise. This is stated in a way that's kind of language and protocol agnostic. What do we want for security? We want that if we have an execution on one side that results in some Boolean judgment, then the same thing is true on the other and vice versa. So we think if this is, as we intend, secure by construction, then this will be secure as well if the adversary isn't managing to tell them apart via returning a Boolean judgment. That's the setup. It's almost, I think, what we want. But unfortunately, here, if M violates the protocol, then so G says, okay, you just gave me something that doesn't work, then the way that we program this would then cause this to terminate, cause the program to die. And over here, unfortunately, that would be happening within the simulator, but the model referee might already have learned enough to be able to give an output to the adversary. And so you would have a little bit more happening over here than there, and so there'd be a sense in which the adversary was telling these two worlds apart. And I think the way to finesse this, which wasn't in our original paper, is to say, well, each time the simulator is supposed to be taking some action, it should respond either by saying okay to the model referee, or M committed an error, and then the errors should be propagated. So here, if M violates the protocol, G notices that it's going to communicate an error on this channel up to the adversary. The same thing will happen there. And I think this is a way of finessing that issue where there was a small difference between the real and ideal worlds. And again, this is, if you look at the paper that we had so 10 years ago at PLAS in Uppsala. So there's a paper called You Sank My Battleship, a case study in secure programming. You can see the paper. You can also see the code in concurrent ML and Haskell LIO on GitHub at this address here. Okay, so that's more or less where we were last time, except I want to remind you of this ambiguity issue in the way shooting works. So here we have the 5 ships. We have the submarine here and the patrol boat there in particular. And suppose the opponent who's shooting at this board first shot at GD, so that's going to be here, and then shot at HC, which is there, and then finally shot at GC, which is that position there. At that point, it's going to be told, well, you just sank the patrol boat. And so the patrol boat, of course, is here. But from the point of view of that 3 shots, those 3 shots, and what the shooter actually learns, this looks exactly the same. So shooting here, shooting there, the patrol boat was shot. There's no way for the shooter to tell the difference between this situation and that situation. Subsequent shooting can disambiguate these 2 situations, but we're not there yet. And so this is just something to keep in mind as we start looking at the implementations in Haskell LIO and concurrent ML. So questions before we go on? Okay, so LIO. This is thanks to Steve, who didn't mention, Chong didn't mention LIO, I don't think specifically, but actually you did mention some information flow control label background in which information flow control labels have both secrecy and integrity components. So LIO has that. It's a library for concurrent Haskell with dynamic enforcement. I should fix this typo of information flow control. It provides mutable variables which can be shared between threads and used for communication. And I'm going to try to tell you enough about LIO to make the rough idea of this implementation clear. You can ask me more questions if you want. So the player interfaces are first of all going to exchange, and this is key, using trusted code, labeled boards made of labeled cells. A labeled cell is an element of this data type that's here. And so it's labeled by a DC label, which indicates both secrecy and integrity. Inside it, it's got the two principles, the originating player interface, the one whose board this is part of, the receiving player interface. The reason that we record these two is to prevent replay attacks. And so there are a bunch of subtle things that attacks that could go on. So this is one of the techniques that we use. There's also just the coordinates of the cell, the position of the cell. And then finally, there's what's called a DC action, which you can think of as a thunk, which if run, will produce an element of this data type, saying that shooting this position will result in a miss or a hit or sinking a given ship. So this is something that you can run. Until you run it, you don't know what the output is of running this action. Okay, so let's imagine that player interface 1 has shared all the cells of its board with player interface 2. There are only 2 cells of the patrol boat here, but imagine that all 100 cell, or well, yes, all 100, let's see, are we doing, no, I guess just the cells, I think just the cells of the ship. No, I guess we're sharing all the different cells. Anyways, but they're just 2 here, but imagine all the other ones are there as well. And then what is this nomenclature supposed to say? This is supposed to be the integrity over here, which is who trusts it. And so it's saying both principles actually trust both of these. The cells were created by trusted infrastructure, and so that's why this could be achieved. So player interface 1 takes its original board, sends it to the trusted infrastructure second, and which produces these labeled cells, and in particular labels the integrity, sets the integrity to be trusted by both. This is the secrecy. It's saying who is able to declassify the cell. So that's the 1. Yes?
I was wondering if this program runs on one machine, or are they on multiple?
Yeah, so the server is running in multiple threads, but on a single machine. A good question. Okay, so this is trusted by both, but the secrecy is 1. So to declassify this, it's something that player interface 1 can do because it has the right permission for doing this declassification. It turns out, well, player interface 2 in LIO could unlabel this. What would happen, though, is that its program counter label would be raised so that it also had 1 as part of it, and its channels that it's trying to communicate on won't allow that. And so if player interface 2 just declassifies one of these cells, it'll basically put it in a position where it can't do any more communication. And so, that's why it can't do that. So suppose it wants to shoot HC, that position, on the board, then what it has to do is actually, right, I should have said one more thing. So each ship has a mutable variable associated with it, which the DC actions, so here and here, of those cells actually have hard-coded within them. So they can when PB is run in one of these cases, these DC actions, they can actually reference, read and write this mutable variable. And that turns out to be key. So if player interface 2 wants to shoot HC, it has to send it to player interface 1. Player interface 1 can look at the integrity and think, okay, this is kosher, this is something I should trust because it has my integrity. It was created by the trusted infrastructure. It has also the permission to declassify this. So it can declassify it, and so that takes the label off. And then what it does, and this is an interesting kind of ripple in the protocol, it runs the DC action. And what the DC action does is it puts the position, so this action knows about the position, puts the position into the head of this. So we're adding things from the left, and so it puts HC into there. It then sends it back to player interface 2, which says, okay, it's still got my integrity as well, and it's unlabeled. And so now it can look inside it and see these details that are here. It knows that the contents of this haven't been modified from when it was created by the trusted code. And so now it can run PB. And what PB does is it looks inside here and it says, okay, this isn't full yet, and so this is a hit. And so I'm going to say that this was a hit. And so this is the response that player interface 2 gets. If it then, when it's its turn again, if it says, well, I want to shoot GC, then it does a similar thing. So this gets unlabeled, declassified. PB is run. GC is added to the front of this, and then it's sent back. And now when PB is run, what the action is doing is saying, oh, this is full, and by the way, my position is at the head, and therefore this is actually sink of patrol boat. Now the cool thing is if it goes back to running this DC action here, then it says, well, this is full, but HC isn't at the head, so it's still going to say that this is a hit. And this is important because it's not entitled, given, so as we saw in that example of ambiguity, it's not actually entitled to know that this cell here is part of the patrol boat. It might not be. It is, of course. We know with our inside knowledge here, but it's not entitled to that information. So that's, yes, that's how this works.
Yeah. Does this have a way of representing those ambiguous situations where you're like, oh, I sunk the patrol boat, but there's, or you're not sure if you sank the, I remember that example with the ambiguous forward state before, and I'm wondering how you represent that here.
Yeah, I mean, so there was that other cell, and so if, I mean, one thing that we can think is that if these were the first two shots that we made, then actually we do know, right, that this is the patrol boat because we haven't done any shooting. If we did that other shot before, then there's ambiguity. But even in the case where these are our first two shots, we're still not going to actually say explicitly that HC is part of the patrol boat. We're going to let the user figure that out from the context, but we're not going to reflect that actually in the protocol. Okay, so that's the idea of this one. And well, so one little ripple here, right, was that we ran the DC action after declassifying before we sent it back. Anyone know, anyone want to give a guess of why that was important? So if we didn't do that, so at the point where we send back that we haven't added this, the position to here, then it's possible for player interface 2 to collect these cells and then unclassified cells and run the DC actions in a different order. It only gets one go at this, but then it could have first ask player interface 1 to declassify HC and then GC. So maybe player interface 1 thinks that's the order in which the shooting is happening, but then it could actually run the DC actions in the other order, and that would tell it that HC was part of the patrol boat. HC was then the one where we did the sinking. And so that would give us information that actually we're not entitled to. And when we come on to trying to construct the simulator, we'll find out that would actually break security because things would be in the other order. And that's an example of the kind of mistake that we made so many mistakes that we caught by the auditing mechanism of trying to construct the simulator and thinking in our heads of why the real and ideal games were equivalent, finding that they weren't, and then patching the definition. Another thing is if we don't include the principles, then we can do a replay attack that can also cause problems. You can give, so when you're sending something, you can send it back one of its own cells. That can cause trouble as well. So this is the LIO case. Okay. So what about the concurrent ML case? The concurrent ML is a library for standard ML. We were using the standard ML of New Jersey implementation. It has no special security features, but Haskell, concurrent Haskell doesn't either. But out of its abstract types and mutable references, we can program up access control, which is what, and rich module system, which is what we did. And so we're going to implement player interfaces using a really different mechanism in concurrent ML. This is how it goes. So again, the player interfaces are going to exchange using trusted code. What? Well, this time, immutable abstract locked boards whose cells can be unlocked using unforgeable keys that are held by the original player. So the trusted infrastructure takes the boards, it turns them into these locked boards, and it gives the originator, the person who actually, the player interface that proposed this board, it gives them keys that will allow all these different cells to be unlocked. But there's another ripple. So there's an abstract type of keys. There's an abstract type of counted keys. There's a way of taking a key and an integer, a counter, and making a counted key. But there actually is no way of deconstructing a counted key. So if I have a key, which is unforgeable, so they could be implemented, for instance, by references, and I have an integer, I can put them together and make a counted key, but if I hand you a counted key, you can't take them apart. So there's no way that you can actually pull them to pieces, deconstruct them. This is the type of a locked board. That's what the boards are being turned into. These are the results of shooting. And there's a locked shoot function. Well, right, let me emphasize again that these are immutable. So in the Haskell LIO solution, we used mvars as part of the definition. So we were using mutability there. Yes?
Type signature for the key and the counted key?
So they're abstract. And so this is an abstract type of keys. And so the relevant operations are here, and I'm just about to talk about them or it. So locked boards are an abstract type, and what can we do with them? Well, once we get them from the trusted infrastructure, we can shoot a locked board, a given position of a locked board, by presenting a counted key. And I'll explain what kind of counted key in a second. What we get back is a new locked board. So this is an immutable data type. So we pass in a locked board, and what comes out is a new locked board, and then the result of the shooting. And what's the check that's done? What you would expect, certainly, is that the key of the counted key is the right one for unlocking this position of the locked board. But we want something more. It turns out that locked boards also have counters. Keys, counted keys, have counters. And if for this to succeed and not produce invalid, it must be the case that the counter of the counted key is the same thing as the counter of the locked board. So there has to be a one-to-one correspondence there. And I'll show you how this works by an example, again, involving the patrol boat. So here, imagine, well, player interface 1 has communicated its initial locked board that was produced by the trusted infrastructure to player interface 2. And the 1 there is supposed to communicate that the counter of this locked board is 1. And, well, player interface 2 has also communicated its locked board, but we're just focusing on one side of this. So if player interface 2 wants to shoot position HC, like in the previous example, what does it do? It just sends this back to player interface 1. Player interface 1 says, oh, okay, well, great. I have a key that the trusted infrastructure gave me, that an unforgeable key that will unlock this cell of this locked board. And so I can send that back, but what I need to do is send it back in a form where it has a particular counter associated with it. The counter that it should use is actually 1, because it should be only applicable on a locked board that has the same counter. And so because these match, and HC, this is the key for HC, and that these match as well, then it can do the locked shoot function and get back what? Well, get back a new locked board, which has now counter 2, as well as the information that shooting position HC in this board resulted in a hit. And now, well, if it wants to shoot GC, it can do the same thing. And now player interface 1 says, okay, we're on to counter 2. So I should take GC and make a counted key consisting of GC and 2. And I can send that safely back to the other side. And now shooting LB2 with this, at this position, with this counted key, the counters match up. And so this time, it's going to say sync patrol boat. And so the point here is that because I can't destruct these things, there's no way for me to replay this sequence in another order. So hold on for just a second. So you might think, could we go back to LB1 and first shoot GC? Well, to do that, we would need GC actually, the key for GC actually paired with 1, which we don't have. And there's no way of taking these counted keys apart. And let me just tell you, so it was some interns and myself, one of my colleagues at MIT Lincoln Lab, we were doing this. As I said, we made lots of mistakes. One of the mistakes was not realizing that we needed the counters. And so there was this point where I was thinking again, how do we build the simulator? And I was thinking, so without the counters, you can absolutely, you can do this shooting in the sequence, but then you can go back to LB1 and shoot, use the key for GC and shoot them in the other order, and then learn that HC is actually part of the patrol boat. But again, the auditing process, it was impossible to build the simulator, as we'll see, given the information that flows to the simulator. So did you have a question?
I was just wondering if I spotted a secret monad with the putting a counter on the keys and you can't take them out anymore, or is it weaker than that?
I don't know. I can think about it offline. So that was the genesis of the counters, that we realized, well, without the counters, because these things are immutable, you can replay them in a different order. You can learn things you shouldn't be able to learn.
So this is not a formal proof, right? You haven't formally proved
No, yeah, so I'm trying to emphasize this, that we just use this so far for auditing, but at the end, we'll talk a little bit about next steps. Yes?
You said there's trusted code that's responsible for handing out these keys. Is the trusted code never going to give two keys with the same counter? And that's why we never get to read them?
Well, right, if we go back, I think I can back out of this. So the trusted infrastructure is not building the counted keys. So you give it a representation of the original board. It gives you back a locked board and all the keys, which are uniquely associated with the different components of that board. So each player interface is getting 100 keys. So it's a 10 by 10 board, I think that's right. So it's getting one key per position, and they're all different because they're unforgeable. I mean, it would be bad, right, if I gave if both player interfaces had overlapping keys. So, and then the process of actually turning them into labeled keys has to be done dynamically because we don't know what order, right, things will be done. So the trusted infrastructure can't give us back labeled keys because then they could only be used in a particular order, and we're allowing the opponent to shoot in whatever order they like. So, and right, I mean, there are undoubtedly other ways of trying to do this. What I'm trying to communicate so far is that it's remarkably hard to get it right. And so having some kind of definition of security, and even for the purposes of auditing, was really, really important. Okay, so let's talk then about how we try to use this in auditing. So let's see. We have this. So imagine that we're in. Yes, we're going to look at the construction of the simulator in the concurrent ML case. In the interests of time, we could do the LIO one as well, but I'm not going to do that today. So imagine that this is the one that we just saw, the locked boards with the counters. That's the implementation that we're talking about here. And M is something, well, right. So we have this trusted infrastructure. We have these abstract types, and M has to use them. So it doesn't have any choice, but it can try to use them in some way that it shouldn't. It can try to learn whatever it can. It can try to cheat within the framework of working with these abstract types and the trusted infrastructure. And M, we want to be able to do the construction of the simulator parametrically on the M. So we don't want to look inside it and think, well, if it does this, then we'll do something. We want to actually build the simulator in a way that's treating M as a black box. So what are we going to do? We're going to visualize or structure the simulator like this. So it has M within it, and it has a part that's communicating with M that we call the supervisor. So the simulator has this structure here. And we want to sandbox M in a way that M thinks it's communicating with G. It shouldn't be able to tell. We're also going to do this very tricky thing that M is using this abstract data type, but within the simulator, we can completely re-implement it, and it shouldn't be able to know. This is how data abstraction should work. So there are these types, and there are this operation, this locked shoot, and we can re-implement this abstract type. As long as the signature is the same, it's going to be able to use this. And this is actually a completely standard crypto technique that you have some real protocol and you can, in the simulator, you can re-implement things however you like. That's perfectly kosher. And so here we're just following in the normal way that we do proofs in crypto. So, so the M thinks it's interacting with the very same, well, with G and using the very same abstract data type that it was down here, except, well, we're re-implementing it. And it turns out we have to re-implement it for a couple of reasons. So, whoops, am I going the right direction? Right, so the first part of this is I want to try to explain why M doesn't learn more than it should be able to. And so this is going to be the picture inside the simulator as things unfold. So we have that supervisor, we have the copy of M that's sandboxed. And, well, M has just gotten the locked board with counter 1 from the supervisor. But if you think about it, right, normally the locked board has within it all the information, right? It's this immutable value. And it has within it, in a way that we can unlock with the appropriate counted keys, it has everything within it. But inside the simulator here, right, we only know what the model referee has told it. And at the very beginning, the model referee hasn't told us anything at all about the opponent's board, right? So this board here, this locked board, is the one that corresponds to the opponent. And, well, the model referee knows it at this point because it's been sent along this channel from the adversary. But over here, well, nothing about that board has flowed in the leakage at all. So initially, this is like a bluff. It's this locked board. It has counter 1, but it has nothing in it. And it's an immutable value, so, well, that seems like a problem. So what we do in the re-implementation is we actually have it pointing to a bunch of mutable variables, one for each position. And these are the positions of the patrol boat again, GC and HC. And initially they have nothing in them because, well, we don't know anything yet. So if M says, well, okay, right. Meanwhile, the model referee is saying, hey, it thinks this is a player. What do you want to shoot next? Well, meanwhile, M is thinking it's my go. I'm allowed to shoot next. I want to shoot at HC. So it sends that across to what it thinks of as the other player interface, which says, oh, well, that's great because I was just asked where I want to shoot. And now the model referee says, okay, well, I'll look at the opponent's board and shoot at position HC and update this board. So that's fine. And I'll say, well, okay, that was a hit. And now what the supervisor does, it says, well, okay, I'm going to patch hit into that mutable variable there, which LB1 has a pointer to all of these mutable variables here. And now, well, you can see what's going to happen. The supervisor sends an appropriate counted key, the key that will unlock exactly position HC, and the counter is 1, so this is consistent. So now M can run the lock shoot procedure, and it will work. But what does it do? Well, it actually consults this mutable variable to say this is what I should return. So I should return hit, like that. And then, well, it unfolds as you'd expect. So meanwhile, the model referee, so the other player, let's suppose, is shot, and now we're coming back to this one. Where do you want to shoot? M thinks it's its turn. So this dance happens. This time, the model referee is shooting position GC, so it's going to say, okay, the patrol boat has now been sunk. That's going to get patched into this position here. And now it's safe to send the counted key that will unlock position GC with the right counter. And so now consulting this position here, we can say, well, okay, the answer for doing that is sank the patrol boat. Now, if we didn't have the counters, right? Let's go back to that scenario where, you know, I mean, I actually woke up at 2 in the morning thinking, oh my goodness, there's something broken here, because my brain was mulling over how to build the simulator. And I was thinking, well, without the counters, or suppose we also could destruct them. Maybe that's easier to think about here. If M could destruct these counted keys, it can take them apart and it can give GC counter 1 and use that to shoot LB1. And well, LB1 at this point, so HC at this point, it's going to say that that's right, the other way around. It's doing GC first, so it's going to say, okay, that's part of the patrol boat. But then it can relabel the key for HC to be 2. It's shooting that 1 second. But let's see. So in that case, it's going, right, sorry, in the, no, right, sorry, in the real world, right, so it's shooting them in the other order. In the real world, it's going to say that this is a hit, and this one is where we sank. But in this one here, we don't actually know for HC that it's part of the patrol boat here. And so we're not going to be able to replicate the same behavior as we got in the real world. So the real world, without the counters, it could do them, it could go back and it could do them in the other order and learn that unequivocally that HC was part of the patrol boat. But we don't know that here. And if we imagine that other cell had been shot first, indeed, it might not be true. So if these were the only 2 shootings that M had done, well, then actually the simulator could figure it out. But that's not what the implementation of the protocol in the real world is doing. Yes?
So looking at the supervisors column, we have these messages like hits and sank patrol boat, but when looking at the ML code, I was under the impression that one needed a locked board in order to get these messages and run it through that function at the bottom of the code fragment. So then how is the supervisor getting these messages?
Yeah, so let's go through that again. So when if I back up to this position right here, so this is the model referee, right? And it has both players' boards within it, and it's saying to this player, where do you want to shoot next? M is saying that it wants to shoot position GC. So that goes to here. And then, well, the model referee knows both boards, so in the clear. And so it can say, well, HC has already been shot, so now you sank the patrol boat is the information that it gives to this player, but the supervisor then says, okay, I can put that into this mutable variable here so that at the point where M can actually needs to access that information, it's magically there. Yeah. So we have to keep thinking the model referee, right, has both boards, and it's this trusted thing that's enforcing the rules of the game. So excellent question. Anything else? Okay, so that's part of the story. There's also a part of the story that M here, imagine that M sends to G something, a locked board, but there's some bug in the protocol, and it somehow manages to conceptually move its ships to somehow, in its interactions with G, if it didn't really commit to a board. So it's kind of playing this game of moving things around as you shoot at its board. So it's playing fast and loose there. How do we know that that can't happen? How do we know that whatever it is that M is sending to G is actually unequivocally, irrevocably committing to a board? Well, in the ideal world, the model referee at the very beginning is expecting this player and that player to send it their board, which it is holding. In other words, that means that the supervisor here at the very beginning is being asked, what is your board? Because from the model referee's point of view, this is a player. And right, the puzzle is, well, how does it do that, right? That so M is giving to S a locked board, but you know, how can the supervisor do anything with that? And so what we do here is the abstract type that is being used inside the simulator, as opposed to the real one, which is here. It actually has two kinds of locked boards, as the kind that we just talked about that point to these mutable variables. But also, it has one where the supervisor has an extra API call, which lets it actually look inside this locked board and pull out the board that was used to create it. So it was being created by, so M thinks it's interacting with the trusted infrastructure, but it's actually a kind of variation on that. And so M gives a real board, has to give a real board to the re-implementation of the trusted infrastructure. And, well, it produces this second kind of board that when it passes this to S can say, oh, great, I can introspect into this thing and I can pull out the board and then I can give it back to the model referee. So now, in the ideal world, at the very beginning of the shooting phase, the model referee actually has this board in its hand, which won't change, by definition won't change. And so over here, if something else happens, if there is some bug in the protocol, well, that'll be something that'll make these worlds look different to the adversary. But there's a little ripple here. So if I'm M, what could I give the supervisor that would really frustrate it in this case? So suppose S has given to M that board, locked board first, the one that's empty, that points to the mutable variables. What's an evil thing that M could do next?
Is there a way to make it like computationally expensive to check that it's on the next thing?
It's something way simpler than that. So I'm S, and I give this empty locked board that points at these mutable variables to M. M can then has to send me a locked board. What could it send me back? Yeah, the same one, right? Whoever said that. It could do a replay attack. So it's sending me back something something that has nothing inside it. So this is probably a bad thing, right? Because then there's no way of doing this extraction because there's nothing even there. It wasn't derived from a board. And so there's a little bit of stuff that has to be done in the real protocol to make sure that a replay attack isn't possible. But this was another one of these things where oh, right, how do we stop that from happening? So it's like, I'll take your question in a second. The story I'm just trying to tell here is that even as an auditing technique, this was just extremely powerful because there's a very precise thing that we're trying to do, build this simulator such that we can imagine running these things step by step and having things that can happen over here correspond to things that can happen there. And so time and time again, we just kept running up against bugs in the protocol that meant that the simulator couldn't be constructed.
I was a little confused about the last point. Is it a matter of data validation to make sure the board actually has the ships on it that it should, or is it, I guess I'm missing in what sense, like, a replay attack?
Yeah, so down here, so where there's an official abstract data type, then G can send M its board, and they're without some kind of ripple in the protocol, M can just send it back if it wanted to. I mean, it's a perfectly reasonable value of that abstract data type. But up here, the problem is that S sends M this board that in the re-implementation of the abstract data type, which was this trickery, right? This thing that doesn't actually have any contents but points at these MVARs. And if the same thing happens as happened in the real world, M doesn't know where it is. It says, oh, I'm just going to replay. I'm going to send back the board I was given. It could do that in the real world, but in the ideal world, if it sends it back, well, it's this thing that doesn't actually have a board in it. It's just, this fiction that just in time I was filling in these MVARs, or the implementation was filling in these MVARs so that when M could actually pull off doing shooting, magically the information was there. So that's the deal, that something can happen in the real world, G sends its board to M, perfectly kosher board made by the trusted infrastructure, M just sends it back. That's fine in the real world, well, without the modification of the protocol that prevents it. But if it happens in the simulator, then the proof, the correspondence between real and ideal goes poof, and it's another, oh my goodness, what do we do about this? So it's not, I'm not going to tell you what the solution was, but it's not very hard. But it's the kind of thing, these are all things that kind of come up in crypto in a non-PL setting all the time.
So is it that the real world would accept it and the ideal world would reject it, or is it that the real world would get stuck and the ideal world would reject it?
So the real world so things down the road may not go very well with this, right? So if G sends its board to M and M sends it back, well, the problem is M doesn't know any of the keys corresponding to that board. So at the point where G tries to, let's see, so G has this locked board, and that came from M, and it wants to shoot some position. If it sends the position to M, M can't, well, maybe M, depending upon the order that things come, it might be a cell that had already been shot, but probably it won't be, because it'll probably be shooting in a different order. And so the protocol, there'll be a protocol violation that'll happen at that point. But before that, here things, right, so we have, this simulator has to cough up an initial board to the model referee, and it doesn't know what that should be. And I mean, I think, there's nothing it can return. I guess maybe it could just make something up, and then I think it's the case that this is not going to go very well, that we're going to end up with a difference between real and ideal. I'd have to think it through again, but yeah. Yes?
So if I understand it correctly, the correctness statement here is that for every possible thing, observation that adversary can make in the real world can be faithfully simulated by the simulator in the ideal world. Is that the...
Yeah, we're actually asking for an if and only if, that So the adversary, remember, is returning a Boolean. It experiments with one of the worlds. It's trying to figure out which one it's experimenting with, and at the end of the day, it returns a Boolean.
Why doesn't it need to be initial again? Well, because we only.
Yeah, I think it's so in the crypto sense, what we do is we say that the probabilities of true being returned are very close to being the same. I think it's the case that left to right is enough, but that right to left makes it possible for us to explain why things break. And I think it's cleaner if we have an if and only if. But an earlier version of this talk, I was trying to finesse that error behavior thing originally by saying that all that mattered was that any run over here that resulted in B, in a Boolean B, that there was a run over here, and there we can sort of finesse the scheduling and make this work. But I think it's cleaner to think, well, any run over here, actually, there's a run over here that produces the same result. It's just easier to think about, and you can, if there's some kind of concrete problem with the protocol, then you can actually explain what goes wrong if you have this if and only if. But it's a great thing to think about.
In terms of like your auditing, it didn't prove that these are the same. How did I'm curious how the auditing occurred. Is this like we checked some inputs and it seemed to be right?
No, it was not based on running. It was based on mentally thinking about the execution. And we could have, I think we could have done it more formally, but in practice I was sort of imagining how this relational argument would go if it was to be formalized. And I was getting to some point where I was thinking, okay, there's a problem here.
Do you actually have code for the simulator, or is it just a mental?
Yeah, so the simulator was just sketched so far. I'll come to this formalization part in a minute.
So forgive me if you sort of said this already, but in this whole auditing process where you're evolving your simulator construction and you're evolving your real implementation so that you can get them closer and closer to everything being secure, were there also times where you're modifying your model referee to actually make everything be sort of mutually compatible and secure?
So the one thing that wasn't right about the model referee, so mostly, right, the model referee, it has the two boards, it's just enforcing the rules of the game. There are no degrees of freedom there except for the error behavior. And Jared is the person who's working with Marco and me on this. And so I think the clean way to think about a protocol violation, so if M says something to G and G says, okay, that's wrong, then it wants to report an error. If the supervisor either reports an error or okay, then we can stop this problem where the model referee sends a bit of information like this, but this just dies. And I'll come back to that in a minute. Does that answer your question?
Yeah, I think the reason I bring it up is because I think when you have all these different moving parts and you're trying to sort of get closer and closer to everything actually finally being secure, I wonder if there are times where you end up actually over-engineering solutions because while eventually, once it is secure, you can prove, or we can hope that you can formally prove the if and only if indistinguishability. I'm wondering if there are times where you actually do have a system where there are times where you actually a simulator does exist, but you just haven't thought of it. And
sure.
So, but we don't have the reverse. We don't have the proving that this is not secure, proving that there is no simulator. So there could be times where you've over-engineered and you've created a more complex simulator and a more complex real implementation than you need. But I imagine that especially in a complex system like this, it's very hard to spot when you've over-engineered. But I guess at the end of the day, there isn't much wrong with over-engineering. Unless you've made
Yeah,
something really
I-
computationally
yeah,
expensive or something like
I
that.
think you're right. In a typical crypto setting, this is the ideal functionality. Getting this is often, I'm going to talk about this in a minute, but I guess we're at an hour now, right? So I've got 20 minutes. That crafting the ideal functionality is hard in general, but here we were really helped by the fact that we already had this, right? That the first thing that I did, you know, working with these interns was I wrote this model referee. And so luckily enough, that's almost exactly what we want, modulo this error behavior. Okay, let me go on a little bit. Right, sorry, yeah, I talked about that, the replay attack. Okay, so let's see. Separating the definition of security from its enforcement, I claim is just huge. That it was, at first, it was just thinking about mutually distrustful player interfaces and trying to figure out what the heck the definition of security was going to be. It was like, I have absolutely no idea. There's all this stuff that M could do. How do we know which of it is okay and which of it isn't? And, you know, simultaneously, I was working on this EasyCrypt project, and I thought, you know, holy shit, you know, just put the two parts of your brain together. And I'm still trying to convince PL people that, you know, that they should try to think this way. So let's see. Right, this is just summary. So far, it's just informal auditing. We found a lot of bugs. Maybe I should be embarrassed that we had so many bugs. Let me go on just a little bit first. That we had so many bugs, but it's actually good for the story of why this was a useful thing to do. There's one issue that I've skirted around, this sandboxing. So there's safe Haskell is what's used in LIO, and it stops a lot of bad behaviors of M. But as far as I know, I haven't gone back and looked at this, about the error behavior. I think M could just cause the whole process to exit. And so really what we want is some way of checking that M is only, it isn't just like blowing up and it's only interacting via the channels that connect it to the rest of the system. In concurrent ML, we kind of had to resort to a manual looking at the code. But you could do all of this clearly with a type system. I'm not sure whether there's a way of tweaking, say, Haskell, for instance, so that you can make sure that it doesn't like run a system call, for instance. This is what we would probably want in this case. Okay, so how do we know that a real ideal paradigm definition says what we want? In general, designing ideal functionalities is definitely something of an art. That's probably an understatement. It's like super easy to get them wrong. Cryptographers learn this stuff in a painful way where they make lots of mistakes. So, and I want to give you an example of something, a mistake that we could have made. So suppose in the real world over here, when M shoots on G's board, that this player here is just told, well, the opponent shot at your board, but not where it shot. You know, it would be a little bit more boring because you can't see how close they're getting to destroying you, but you could do that. And well, so here we wouldn't, the model referee wouldn't be saying where this player shot. It would just let this player have a go and then reverse the roles. But the problem here is that maybe M has done certain shooting, and there's certain things it should have learned, right, about G's board. But in the model referee, because nothing's being reported up this channel, the simulator player could shoot other places. And the model referee would say, oh, that's cool. You know, it's your turn. You can shoot this sequence of positions. they're not the ones that G is learning about, but, and so G thinks that M has only learned about these positions, but actually M has learned about other positions because of a bug in the protocol, and the model referee can support that, and so we have security. And so by the simple mistake of not including where the opponent shot as information that's reported here, then we end up with, if we had a bug in the protocol, then we could end up not noticing it. And so this is just a classic thing that shows up in crypto all the time, that you have to stare at the ideal functionality and be think really hard about it. Does it actually capture what you want? It's easy to get it wrong, and so, well, we didn't get this one wrong, but we could have. Okay, so let's see. So what are our alternatives to the real ideal paradigm for defining the security in this setting or another one is a really interesting question to think about. That there's a downside, I think, to the real ideal paradigm, which is precisely that thinking in terms of this procedural way of defining the ideal functionality, it's hard to get it right. And so maybe it would be really great if you could just describe what you wanted using some kind of OR logic or something like that, but I don't know how to do that, but you might. And so I think this is an interesting direction. Are there alternatives that would be easier to think about than this approach? This approach has worked great in crypto. Maybe there's something for PL that would be easier. Although, the cryptographers, if there was something better, maybe they would have thought about it. So I'm not sure. This whole enterprise of, in the case of Battleship, that well, there was this trusted referee. It was really simple, and instead we substituted this hard thing that sort of reduces the trusted computing base. It would be nice if these solutions are kind of complicated. It would be nice if we could have a way simpler solution. Maybe you can think of one. Was this useful? I don't know. I mean, it's a fun thing to think about, at least. Why didn't we really use information flow control? It's like when we started out with this project with interns, we were trying to evaluate LIO as we were in this testing and evaluation role at Lincoln, and we thought this is like this classic thing that Battleship, there's this GIF implementation that you were part of, or which uses all these information flow control annotations for Battleship. So we thought, oh, this is like a classic example, except we have a CML plus access control solution here. In the end, everything gets declassified. You can use LIO to enforce as an enforcement mechanism, but I'm not sure it's fundamentally an information flow control thing. Some things clearly are. And so trying to understand, when do you really need information flow control? That's another thing to puzzle over. Right, okay. So this work that in formalization, we would, way back 10 years ago, I was thinking, well, if I ever had time, it would be lovely to try to formalize this stuff. And it's nice that Jared and Marco and a colleague of ours at RIT are now thinking about this. It's not super easy. I think, Jared's been working on something that's even simpler, and I think we'll get there. But these proofs are maybe not really easy to do, and so that's an interesting observation. We need a lot. We need something like Iris, but with types, and anyways, we'll see. But if you were enthusiastic about this, you could try to compete with us. Right. So I've got a summary after this, but Any questions before we go on? You had a question, yes?
So you spoke about auditing and how it helped you construct the simulator. What do you mean by auditing? Did you look at logs or did you...
Right, I think someone asked that, and what I said was I played a mental game where I imagined running. I mean, so I do easy crypt proofs, I do relational proofs. I was basically thinking, okay, if I'm trying to do have a relational invariant, and even though the adversary has to interact with one of these systems all by itself, that doesn't mean that when you're thinking about a proof that you can't think about it as a step-by-step thing where the two worlds have this invariant holding, and then they do some internal steps, some tau moves, and then they get back to a point where you're in the relational invariant. And so I just ran that through in my head and found an embarrassing number of problems. So that's the answer to that question. Other questions? Yes?
Going back to the locked board type, is there any connection there to like the sealed pi calculus or lambda calculus with seals?
Maybe. I mean, it's if that's a way. I mean, so it's an abstract type, and so I guess at least in that sense that I don't know. I'm not sure I have a deeper answer than that. More questions? Okay. So just last slide. Well, right. First of all, thank you. Thank you for all the questions and attention. It's been fun. This has been a blast. I've been really happy to be here. And I'd be happy to talk offline. I'd be happy to talk. So if you go away and you continue to think about this stuff and you want to talk about it, I'd be especially interested in, or maybe you figure out some stuff and you publish a paper. I'd love to know if you were influenced by learning about the real ideal paradigm. We could talk about. I mean, we have a couple minutes.
10 minutes or so.
Sorry, 10
Around
minutes?
10 minutes, yeah.
Yeah, so we could talk about anything, but here are some possibilities, and if everyone is just worn out, we can invite Paul down to do his closing summer school comments early. But what do you So I guess so we're popping up to the top. Real ideal paradigm, what do you think of it? Do you think it's useful? Whatever. Yes, Laura.
My special interest, I'm wondering, is there a special way that you represent like computational costs? Or is it like, I know in functional languages you can just count the number of function calls and that gives you a reasonable asymptotic estimate, but I'm wondering how like script could do that.
Yeah, so the question is theoretical crypto is absolutely talking about the efficiency of adversaries, and what I emphasized when I was talking about EasyCrypt is that, well, sometimes, like in the second example, it just didn't matter. So we imposed these budgets, and which in the first example, the NCPA example, those limits were like that. And there, to some extent, raw computation didn't do anything because there were some imposed budgets. But if we take something like trying to tell a PRF from a TRF, there it matters. And the thing that I love about EasyCrypt, but it's possible to not love it, I guess, is that we have constructed adversaries' abilities to win some game appearing as formal terms in the upper bounds, and we just don't have to think about it. When we look at the upper bound, we can impose some idea of how efficient the real adversary is. When we're trying to think, do we think that maybe this bound is acceptable? But we don't have to do that. We have a theorem anyways. But how would you, if you did want to talk about the cost, it's kind of murky because, in my opinion, because we're working often with abstract entities so to be honest, I don't really know how to think about that. So you have some Diffie-Hellman group, and you want to say that computing discrete log is hard, but we axiomatize the group in this abstract way, and we do a proof that works no matter what the group is. And so how do you talk about how hard that is? You could implement it using some concrete way, but how do you know that there isn't a better way to implement it or whatever? And so I don't know. Cryptographers think about probabilistic polynomial time on a Turing machine. I'm happy that I don't have to do that. And to be honest, I don't really know how to even think about it in the presence of these abstract things. That if you want to implement everything as bits, then and spell out everything, then of course it's easy to count cost, I guess. But if you don't want to do that, then how do you talk about cost? I don't actually even really know. But I've been happily not. I don't have to answer that question because the theorems I prove are true, independent of whether you like the upper bound, which does have to do with questions like that. A good question. Yes.
I was wondering if there is a methodology to make these ideal games, because it seems to me that it's almost ad hoc, and I don't know how you would compose a protocol which uses an ideal game and to build a bigger system.
Yeah, I mean, so the question is, well, is there a methodology for building these ideal games? In crypto, I would say it's not. It's an art form. But is there a way to do modular analysis? Absolutely. There's this other project that I'm involved in for universally composable security. We're trying to mechanize proofs. And in UC security, when you prove a real ideal protocol security result, you do it in a very general way where you can plug that into a bigger system and know that you still have security. And if you look at my GitHub, you can see some work on that. I just originally I said I would talk about that as well, but I realized pretty quickly when I was planning this that was a non-starter. But so the modularity part is something. It's hard. You can have real ideal security that doesn't compose. So the standard definition doesn't work, but this more general notion of UC security does compose. That part, there's a solution to, but the part of how do you craft an ideal functionality that's really what you want is like, this is what people learn by working with a mentor and studying a bunch of examples and getting better and better at kind of predicting whether what they've crafted is what they want. But still, you look at some theoretical crypto papers, and there are these absurdly complicated ideal functionalities, and you have to wonder, do they do what they want? Well, one of the things we can do, by the way, in our mechanized UC is we can express all of these UC designs in a DSL, and we can actually experiment with them, which at least lets you get a little bit more confidence that they do what you want than writing down a bunch of tables in LaTeX. Maybe last question. Yes?
So what you put possible alternatives or what is it the slide what are those in your head?
Yeah, I mean, well, so I'm fishing for this, that I don't feel like the PL community, so there may be, so if you take this battleship example, the GIF annotations in this Java information flow told, in my reading, they told someone what to pay attention to. So there were a bunch of annotations, and you could think, are these the ones that I want? But I don't think that they were a security model. And is there is there a way, I mean, what the holy grail here would be something more like core logic, something that used logic, something that was less procedural. So the ideal functionalities are these things that you run, right? But is there another approach that will capture the ideas that we just talked about today, express it in some other way? I would love to think that the answer was yes. I don't know the answer to that. So I guess, so Stephen this morning was one of the Stephens, the one about probabilistic programming, was saying, go away and, and do cool things. If you can go away and think, okay, let's take Ali's example and let's describe security in this way that isn't kind of isn't procedural. Ideal functionalities are things that you run. That would be great. I think that would be a contribution. You do that, do it in a way that's even for this particular example, you could probably publish that. Okay, we should stop, I think. Thank you so much.